I am live. Can you help check if I'm live? I'm pretty sure I am. Take a look at my channel real quick. Am I live right now? Yes, I am live. W. Great. I'm sending it here. Hello. 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 Nice. Just gotta do an audio check. Hello. 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 1, 2, 3. 1, 2, 3. Okay, yeah. Okay, yeah. Okay. Okay. I guess I'll just get my thoughts together first before we start. Okay. Yeah. Is the camera angle fine? I'm gonna keep the camera angle like this. The thing is, I don't really know what what marker to use. I'm gonna write that for the meantime. Do 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 do. Wow, you can hear my typing. Okay. I guess I'll start in a bit. 1 more minute. Excuse me. Okay, I guess I'll start. So, hello. Welcome to General Chemistry with Antimatter. So, this will probably be one of the last batch, or one of the last videos I'll be making regarding tutoring. Or at least within this setting. So, without further ado, let's just get straight into the teaching. So, with the topics we've been discussing, we have been discussing the colligative properties of solutions, which is just a fancy way of saying there are different types of characteristics and properties when it comes to mixing solutions together, or mixing solutes and solvents. So some of these can determine how it affects the boiling point and the freezing point. So we'll be discussing more about that later. So the definition for it is this: properties of solutions that depend on the number of solute particles present. Meaning, depending how much solute is in the solution, the properties of the solution will be changed, it'll be affected. So, let's have our first example. One of these properties is called boiling point elevation. So, I will write this down. I'm going to be conserving my marker because I'm not quite sure when this will dry out. But this is boiling point elevation. This is going to be our topic. So the definition of it means that when you add more solute, or when you add more things to a solvent, to a mixture, the boiling point of that solution increases. So for example, the boiling point for pure water, H2O, is 100 Celsius. If you were to add something to it, let's say you're going to add salt, or you're going to add literally anything else, the boiling point will increase. Maybe it will be 101 Celsius for it to boil, or 102, or 103, so on and so forth. However, we are going to be discussing a formula that can help us find out how much the boiling point increases based off of given variables. So, this is the formula of it. So the change of, or the boiling point elevation rather, which is represented by this, is equal to I times Kb, which is the mole boiling point elevation constant. The I is the Van Hoff factor, but we'll talk about that later. And M is the molality. So I will explain what these variables are. Okay, so first let's talk about the Van Hoff factor, which is the I. So it is spelled like this. Van Hoff, or yeah, Hoff factor. Oh, okay, factor. So it is spelled like that. So the definition of the Van Hoff factor is it's basically a measure of how many particles a solute produces in a solution compared to the number of units dissolved. Now, I don't know exactly how to dumb that down, but you can just search it up and interpret it your own way. Now, I'll be teaching you how to get the Van Hoff factor based off of two scenarios. So usually, most of the time it is specified whether the value is 1 or something else. So if your solute is specified as non-volatile, it means that your I is equal to 1. Your I is just equal to 1 if it is non-volatile. However, if it isn't specified, if it is non-volatile, we're going to have to do something else. So we can actually find the Van Hoff factor simply by just counting the subscript. So for example, if we have a compound of this, NaCl, sodium chloride, NaCl naturally have a subscript of 1 and 1 because their ions balance each other out. They crisscross. So if you just count these together and add them up, that means their I value is equal to 2 because there's only 2 subscripts. If we have another example, let's say we have aluminum sulfate. So we're going to have Al, 2, then parenthesis SO4, 3. Now the I value of this is equal to 5. Why is it equal to 5? Well, we're simply counting the subscripts. Again, we're counting 2 and 3. Now, why aren't we counting the 4 that is connected to the oxygen? Well, that's because this is a polyatomic ion, meaning it's technically counted as one variable. SO4 is represented as sulfate. So you can have it represented as just one singular variable in this context. So that's why you don't count it. So any polyatomic ion, you don't count the subscript connected to the oxygen. You mainly just count the subscript outside of the parenthesis. So that's how you get your Van Hoff factor. Next, you have Kb. Now Kb is the molal boiling point, or molality boiling point. Elevation constant. So just from this word alone, constant, it means that the value doesn't change at all. It depends on the solvent that is given. So some solvents have different constant values, some don't, some differ little bit by little bit, but it is almost always given. So you don't have to worry about this. And lastly, we have M, which is molality. Now again, molality is a measurement of how many moles there are per kilogram of solvent. So how many moles of a solute are in a kilogram of solvent. So for example, I want to know how many moles of salt are in 1 kilogram of water. So then you're going to use molality, which is represented with this formula. So molality is equal to moles of solute divided by kilograms of solvent. Okay, so this is the formula for molality. So in order to get the molality, it's either given by the problem. It will state that m equals to 1, m equals to 2, or you're going to be given the mole of solute and the kilogram of solvent. But what if we have a problem where molality isn't given, nor is the mole or the kilogram? So we will dive into that in a little bit. I will just further explain this. So this is how you get the change or the boiling point elevation. However, this only describes us how much it increases. It doesn't give us our final temperature. To get our final temperature, we just need to find the boiling point of the solvent plus this, which equals our new boiling point. This is going to equal the new boiling point of the new solution. So let's have an example right now. Okay. So I will only mainly be doing 1 or 2 examples per problem because this might take a while if I take too long. Okay. So we are given these things. Okay, this one looks pretty easy. So we're given the molality, which is equal to 1.5 molal. The Kb is a constant, so again, it never changes. 0.51 degrees Celsius per mole. Lal, I equals 2. So the Van Hoff factor equals 2. So these are our given. Okay. This is our given. So these are what the problem has described. I don't have the exact problem, like the word problem, but this is what's given. Now we are required to find the boiling point elevation and as well as the boiling point of the new solution. I shall also say that this was given in water. The solvent is water. So we could say that the boiling point of H2O is equal to 100 degrees Celsius. Okay, so this is the boiling point. This is all the given, and these are the required. Now for the equations, we can use this. We can use the formula for the change in boiling point, the boiling point elevation, which is equal to A times Kb times M. And then we also have the formula for the boiling point, which is Bp equals Bp of H2O plus the change in boiling point. So these are the 2 equations that we'll need, the 2 formulas. Now let's actually implement it into the solution. So first we want to get the boiling point elevation. So in this case, I will just erase this so we have more space. So in this case, this is how it's going to work. I will just flip it a bit. I'll flip it back the way. So we're just going to substitute it. So I is equal to 2. Kb is equal to 0.51 degrees Celsius per molal. And then our molal is equal to 1.5 m. So then we simply just multiply together. Just put it in your calculator and multiply it together. Now, when you're doing this, your units will cancel out because the m is found in the denominator and you're multiplying it as well. Now, according to my notebook, which I assume is correct, the answer is this. The answer is 1.53 degrees Celsius. This is your boiling point elevation. So now that we have this value, we can then do the formula for the boiling point. So in this case, we just simply add. So 100 degrees Celsius, this is the boiling point for water. plus the change in boiling point, which is 1.53 degrees Celsius, you are going to be given a value of 101.53 degrees. And that is your boiling point. Like so, boiling point equals 101.53 degrees Celsius. So that is how you find your boiling point. Okay, so pretty simple, right? You just substitute the values and you multiply, and then when you're done multiplying, you add. Very straightforward. However, I was told to do an example where you're going to have to do deriving. Now, if you're not familiar with the term deriving, this just simply means manipulating the formula to get a desired output. So for example, let's say we were given these things instead. So this applies to everything in math. Okay, I'll just teach you some basic rules. So if we have a pyramid, let's say this. I don't know how to describe it using other terms, but let's say you have X, Y, and Z. So usually when you have a pyramid like this means X equals Y times Z. Y equals X over Z. And Z equals X over Y, right? That's how that pyramid is interpreted. But it doesn't always have to look like a pyramid. Sometimes you'll see it in more common contexts. Like, for example, let's say we're given 1 mole of oxygen is equal to 16. Oh, oopsies, sorry. Oh, yeah, sorry. 1 mole, yeah, sorry. Okay. Oopsies. 1 mole of oxygen is equal to 16 grams of oxygen divided by 1 mole of oxygen. So it looks like this. You can apply the same formula. You can apply the same thing. Because this is just your mole here in this value. You have your molar mass in this side. And then at the top, you have your atomic weight, which I'll put as A.W. Atomic weight. So this is I won't say it's a cheat code, but it's something to keep note of. You can find these sorts of pyramids everywhere. You can reverse it the same way you do. The mole is equal to the atomic weight divided by molar mass. The atomic weight is equal to the mole times the molar mass. And you could also say that the molar mass is equal to atomic weight divided by the mole. Yeah. So that's just other ways that you could see it. But let's say we have an actual word problem that involves deriving. Let's say molality isn't given, and you're also not given the moles, nor are you given the kilograms of solvent. So let's have an example. Let's say instead of being given the molality, we're given everything else but it. So Kb is still equal to 0.51 degrees Celsius per molal. I is equal to 2. Let's say the change, or not even the change. Let's say that the initial temperature, boiling point is equal to 101.53 degrees Celsius, and that the boiling point of water is equal to 100 degrees Celsius. Now, we are told to look for the molality. How would we do that? Let's say we're told to look for the molality. We don't know what the molality is. We also don't know what the boiling point elevation is. How do you do that? Now, this is another way you can interpret math symbols. Now, when you see the sign delta or triangle beside the variable, that just means change. You're looking at the change, or the way that the value, the change rather, which can also be deducted from this formula. So if you have delta x, this is equal to x final, so the final result of the variable, minus the initial. So in this case, in this context, the final value would be our BP, right? So our change, or our boiling point elevation, is equal to our boiling point of the new solution, which is 101.53 degrees Celsius, minus the old, or the initial value, which is the boiling point of water, 100 degrees Celsius. Now, when you subtract this, you'll be given the final value of 1.53 degrees Celsius. So this is how you find the change in boiling point if you're given two temperatures. If you're only given two temperatures, nothing else, that is how you get the change in boiling point. So now we have a new value, which is 1.53. So change in boiling point, or the boiling point elevation, is equal to 1.53 degrees Celsius. Now that we know this, let's try to get the molality. If we look at the equation, it is the change, or again, the boiling point elevation, is equal to I kb m. So this is a formula. Now again, we need to know how to manipulate or derive certain equations. How do you do that? Well, it's by doing some simple logic, I guess. Notice how when it comes to operations in math, the four of them, addition, subtraction, division, and multiplication, seem to be the opposite of one another. If I add 2, subtracting 2 is going to do the same thing. If I multiply 2, dividing it by 2 is going to reverse that effect, right? It's like the opposite. So this is what we're going to do. We need to isolate m. But if you look at m, it's grouped by I and kb. Or rather, it's being multiplied with I and kb. So in order to get rid of them, we need to divide both sides with I and kb. So when you do this, it cancels out. The m becomes isolated, while this remains the same. So your final equation to get the molality is this: the boiling point elevation divided by the Van 't Hoff factor multiplied by the molal boiling point elevation is equal to the molality. So that's how you derive equations. It goes the same thing with the kb and the I. You just divide it if it's being multiplied with. If it's being divided, you multiply it. So if I want to revert this back, I just multiply the whole equation by I kb. And that's how you derive certain variables. And that goes for any problem. That goes for the next topic as well, which is freezing point depression. So it is just like boiling point elevation. However, instead of the value going up, it goes down. So I'll just write it here so that we know the topic. Freezing point depression. Okay, freezing point depression. Okay. So, just like the boiling point elevation, this covers how adding solute can actually change the freezing point, or the threshold at which something freezes. So, in this case, rather than it elevating, the temperature decreases, meaning it requires a colder temperature for it to freeze. Again, you add ice, or you have water, freezes at 0 degrees Celsius. If you were to add more stuff to it, it'll take more cold. It needs to be a colder temperature for it to fully freeze. So again, we have another formula that expresses this idea quite well. And it is actually very similar to the boiling point elevation. It looks like this. So it is Tf equals I, Kf, and m. So all we changed was the freezing point depression. So this is the freezing point depression, or the change in freezing point, with Kf still being the molal, the molal, the molal freezing point depression constant. Again, it depends on the solvent and whatnot. Okay, little break. I just need to get some water. Hold on. Give me 30 seconds. I also need to get something. Yes, I am AFK, hold on. My laptop's about to die, and I do not want it to die, so I just got my charger. Okay, anyways. Alright, so this is freezing point depression. Again, a mathematical expression that expresses how the freezing point of a solution can change based off of how much stuff you put into it. So again, let's say I have pure water right here, which I do. If I were to add random stuff into it, like Silver Swan soy sauce and KFC's 11 herbs and spices, it would take more iced energy or cold or colder temperature for it to fully freeze. Okay, so again, we have very similar variables. This is still the Van 't Hoff factor, so we're still going to be counting the subscript. This is still your molality, so you're going to need to find how many moles of solute are in your kilogram of solvents. The only things that change are the constant and what we're looking for. So since the concept is still quite the same, I'm just going to jump straight into a problem, an example problem. So again, let's say we have this given. Let me erase this formula. So we're given M, which is equal to 1.5 molality. You're given your Kf, which is equal to 1.86 degrees Celsius per mole. Yeah. And then we're also given our I, 2, and our freezing point of H2O is equal to 0 degrees Celsius, right? That's the freezing point of water. So, what are we looking for? We are looking for, well, in the word problem at least, we are looking for two things. We are looking for our change in freezing point, as well as the freezing point of the new solution. So again, we're just going to be using the equations that we know. So that would be the change, or the freezing point depression, is equal to I, Kf, M. And our freezing point is equal to the freezing point of H2O minus the change of freezing point. So these are the formulas that we'll be needing for this exact problem. Okay, so we're simply just going to substitute the values since we already have them here. So let me just erase this and put the solution here. So again, the freezing point depression is equal to I, which is 2, times Kf 1.86 degrees Celsius per mole times the molality, which is 1.5. Signs cancel out, and you'll be left with this value, which is equal to 5.58. 5.58 degrees Celsius. So this is the value you'll be given. Now that we have the freezing point depression, or the change in freezing point, we're simply just gonna find the freezing point of the new solution by doing this. Equal to the freezing point of water, which is 0, minus the new, or the change, which is 5.58 degrees Celsius. Meaning that our new freezing point is equal to negative 5.58 degrees Celsius. Just like that. So that is how you find your freezing point depression. Again, if you're given things that are incomplete, or it seems incomplete, again, there's a change sign. So you could just do final minus initial, or if you're missing your molality, you could just derive it, manipulate the equation, so that you can get the desired variable that you want. So these two, freezing point and boiling point, they go hand in hand, since, as you can tell, the formulas are quite identical. So since we're done with these two, we are officially halfway through the entire quarter. So there are only a few things left, but we're going to have a bit of a reviewer. If you guys are familiar with Dalton's law, which requires getting the mole fraction, the freaking pressure per mole, then we're going to be using that again. When it comes to the vapor pressure lowering, this occurs when a non-volatile solute is added to a solvent, reducing the solvent's ability to evaporate. So it makes the solvent have a hard time turning into a gas for whatever reason. It also says that the greater the solute particles are, the lower the pressure. So basically, the more solute particles, the lesser the pressure there is inside. Okay, or the lesser the lesser the pressure for each mole. Okay, so let's have the formula given here. So it is saying that the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Okay, so again, the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. So there's only really two variables that we need. This formula is actually one of the quicker ones, since again, there's less that's given. So mole fraction just basically means how many of the moles in the solution is the solvent, or is this specific thing. So if, for example, I had 3 moles of oxygen, 5 moles of nitrogen, the mole fraction of oxygen is like 3 out of 8, because 3 out of the 8 moles are oxygen. It's pretty straightforward. But let's say we have an example here. Again, so we're going to try to find the mole fraction of oxygen. And let's say there is 3 moles of oxygen and 5 moles of nitrogen. So the formula would just look like this. 3 over 3 plus 5. Because we're just going to find what we're looking for. And then on the denominator is what we're looking for plus every other mole found in the solution. So this will just equal to 3 over 8. So that's how you get mole fraction. And then when it comes to the vapor pressure of the solvent, for the most part, it is given. in the problem. Now, it is usually given in any unit. It could be in atmospheric pressure, it could be in mmHg, it could be in torr. What matters is that your answer should be the same unit as what's given. It'd be weird if you're given atmospheric pressure and then you're gonna switch it to mmHg. It doesn't make much sense. But anyways, so let's move on to an example problem so it's easier to understand and conceptualize. So let's say we are given 1 mole of NaCl, or the solute, mole of solute, which is NaCl, and it's equal to 1 mole. Then mole of solvent, which is H2O. This is equal to 2 moles. And then we're also told that the pressure of the... Oh, sorry. I'm writing down the wrong things. Okay, let's just say that it's... Here we go. 1.75 moles. And then also 55.56 moles. Okay, so now that we're given these moles, we are also given our vapor pressure of solvent, which is equal to 23.6 torr. Okay, so using the formula that we had, it was the mole fraction of the solvent times the vapor pressure of the solvent. So first, let's find the mole fraction of the solvent, which in this case is this, the 55.56 moles. So this is going to be our B, and this is going to be our A, so it's easier to understand. So our mole fraction of B, which is H2O, is equal to our mole of solvent, which is 55.56 moles, over 55.56 mole plus the other one, which is A, 1.75 moles. So this will be simplified into hold on, let me do the math in my head. 57.31, if I'm not mistaken, 57.31 moles, which will equal to 0.97. Oh yeah, the mole cancels out. So there you go. So once you're given this value, 0.97, you're simply just going to multiply this with the vapor pressure of the solvent. So you're literally just going to do this. 0.97 times 23.6 torr. Oh yeah, this is what your PF solution equals to. So once you have this, your vapor pressure of the solution is equal to 22.89 torr. And that's literally it. You just multiply it again and again and again. So you get the value, you divide it, find how much of the moles are the solvent. Once you're done with that, multiply it with the pressure, and then that's it. That is all you need to do for this topic. Very, very straightforward. Now, we have 2 final topics to talk about. Actually, that's a lot. We have a bit more than that, but I believe it's more straightforward than the other ones, because formulas required for it is actually pretty easy. So first, let's talk about osmotic pressure. This actually doesn't have a formula, but the definition of it is the requirement or the threshold or the minimum pressure needed to prevent the flow of solvent molecules through a semi-permeable membrane. Now, what does that mean? I'm not so sure, but think of it as just the minimum pressure needed for for what? A solute? Oh, a solvent to flow through something. A semi-permeable membrane. So the keyword is just the minimum pressure needed, and also semi-permeable membrane, which is here, a thin barrier, a thin biological barrier that selectively allows specific things to go in and out of it through osmosis or diffusion. So that's why it's called osmotic pressure, because it involves osmosis. Okay, anyways, that's just the definition that's required. We have a little bit of a collaboration here with thermodynamics and chemistry. So yes, physics and chemistry. Let's have a bit of a throwback. The first law of thermodynamics. Let's take a look here. So the first law of thermodynamics states that, or rather the law of conservation, states that energy cannot be created nor destroyed. It can only transform through different forms. So let's say you have mechanical energy that can be turned into electricity, can be turned into kinetic energy, so on and so forth. It can be turned into a lot of things because it never gets destroyed, nor does it get created. Okay, so let's say, sorry, this isn't, I'm actually not quite sure if this falls under the law of thermodynamics, but this involves heat engines and system. So this involves the heat and work, like a relation between that, and how we find the change of internal energy. There you go. This is the formula for the change of internal energy. So U, delta U equals Q minus W. Now Q over here is equal to heat, while W over here is equal to work. Very straightforward. Now the only things that could change is the sign. So if heat is added to the system, or it's being added to an object, it is positive. Heat added. And it is minus if heat is released. Then, for work, the work is positive if it is done by the system. Oops, sorry. Done by system. And it is negative if it is done on the system. So just keep this in mind. So you're going to be changing the sign here. So if it's negative W, this will basically just be a plus W. If it is plus W, it's going to remain negative. If the heat is released, you change the sign of the Q. It's just like that. It's pretty straightforward. As long as you read the problem properly, this should be a cakewalk. So since it's really just subtraction, addition, subtraction, I don't think I need to do an example since it's pretty straightforward. Okay, now let's go back to some definition of terms. So in this topic of thermodynamics, we have things called systems and surroundings. Now a system is basically the thing that's being studied, or this definition of it, the part of the universe under study, while the surrounding is literally everything else, or its surroundings, its environment, what's around it, right? Surroundings. Now there are different kinds of systems. There is an open system, which is an exchange of both matter and energy with the surrounding. So this could be like a boiling pot with the lid open. It's exchanging energy and as well as matter. A closed system is basically like a closed flask, a closed bottle. There can be an exchange of energy through the loss of temperature, but there's no change of matter. Now, insulated systems mean that there's no exchange whatsoever. No exchange between energy, no exchange of matter. This can only happen in like vacuums, where literally nothing happens inside it. So again, an open system, change of both matter and energy. Closed system, change of energy only. Isolated system, Nothing. Oh, yeah, isolated system. Nothing. Okay, another term. Thermal chemistry. Thermal chemistry is a theoretical branch of chemistry that studies heat changes in in chemical reactions. So it's just the combination of thermodynamics and chemistry. So thermodynamics is focused on the transfer of thermal energy, and chemistry is more on the study of matter and its reactions. We just combine the two. That's it. Then, under thermal chemistry, we have something called calorimetry. Actually, I don't know if this is under thermal chemistry. My apologies, my notes are a little scrambled. But there is something called calorimetry, which is a technique used to measure heat changes during physical and chemical processes. Again, it is a technique used to measure heat changes during physical or chemical processes. So when these processes occur, usually they can be defined or categorized with two terms. It is either exothermic or endothermic. An exothermic reaction basically means that heat is being released from the system. The system is releasing heat to its surroundings. So a good exothermic example is what's a good idea of an exothermic example? It's like when you have a burning hot cooked chicken. If you have a cooked chicken and you open it, if you tear open the skin, you'll notice that smoke is coming up. That is exothermic because it's releasing heat. Another idea is an ice cube that is melting. When an ice cube is melting, when an ice cube is freezing, rather, an ice cube is freezing by releasing heat to absorb more freezing energy. So an ice cube freezing can actually be an example of an exothermic reaction. Now an endothermic reaction is the opposite. So if an ice cube melts, that's endothermic because heat is being added into it. So if it's absorbing heat, then that is considered an endothermic reaction. Okay, so now we're going to go back into the final two formulas in this video. And they're both actually super similar. So first is specific heat capacity, or specific heat rather. So the formula of this is quite straightforward. It is, let me write it down first. Oh yeah, so specific heat basically describes the amount of heat required for the temperature of 1 gram of the substance to increase by 1 Celsius or 1 Kelvin. Again, it is the amount of heat required to change the temperature of 1 gram of a substance by 1 Celsius or 1 Kelvin. So the formula for this is Q equals mc times the change of T. So again, this is mass. Let me write that there. So this is mass of the object in grams. This is the specific heat. Now usually this is also given. The unit is actually pretty interesting. And then the change in temperature, which is this, is, well, yeah, temperature. So these are the only variables here. Again, we have the sign, the delta sign, which just means if you're not given the value itself, again, the final temperature minus the initial. So let's have a given here, for example. Our given is this. Mass equals 250 grams. Then we are given two temperatures. Temperature 1 equals 20 degrees Celsius, and temperature 2 equals 60 degrees Celsius. We are also given our C, which is the specific heat. It is 4.18 joules per gram Celsius. Okay. So this is the given. These are all the givens, and the only thing that is required is the heat in joules. There's the only thing that's required. So again, we can use the equation Q equals mc delta T. And also, delta T equals T sub 2 minus T sub 1. There you go. So, to get the value of the change in temperature, we're simply just going to do T sub 2, which is 60 degrees, minus 20 degrees. And it'll be given 40 degrees. So this is our change in temperature. 40 degrees. Okay. Sorry for that technical. Oh, okay, hold on. Hello. Okay, sorry for that technical difficulty. My phone had a notification that somehow blocked the whole stream. Okay, anyways, hopefully I didn't miss that much. I'll just recap. So we were given 250 grams as the mass of the object, 20 degrees Celsius for the first temperature, 60 degrees Celsius for the second temperature, and our specific heat, or the C, was equal to 4.18 joules per gram Celsius. Now we are required to find the heat in joules, which is Q, and we just simply use the two equations listed here. Q equals mc times the change of temperature, and the change in temperature is equal to T sub 2 minus T sub 1. So I simply just got T sub 2, which is 60 degrees Celsius, subtracted it by T sub 1, which is 20 degrees Celsius, and we got 40 degrees Celsius right here. So plugging all the variables in, all the values, we substituted it, we canceled the signs, and we got our final answer, which is 41,800 joules. Now, the answer can actually tell us something. If it is positive, this means that heat is being absorbed. It's being added to the system. This means that this reaction is endothermic. Again, it's being absorbed. However, if the answer was negative, that means that this reaction was exothermic because it was releasing heat. Pretty simple. Now that we are done with this, we are left with one last topic. Now that last topic is also related to this. It is just called heat capacity. Now this is almost the exact same as specific heat. The only thing that's missing is the mass. So it's just C times the change of T. The reason why there's no mass is because heat capacity only talks about the amount of heat required to raise the temperature of a substance by 1. Not 1 gram, the entire thing. So that's why there's no mass. That's why it's just asking us to get the general amount of heat. So, since this is actually much easier to do, I'll just do a given. So the given, I'll just put this as the equation. The given is T sub 1 is equal to 120 degrees Celsius. T sub 2 is equal to 80 degrees Celsius. And our C is equal to 850 joules per degree Celsius. Now our required is Q. We don't know what Q equals to, right? Oh, and that's my dog. So now that we have this, we're simply just going to do a quick solution. Now solution, let's find the change of temperature first. So the change of temperature is equal to T sub 2, 80 degrees Celsius, minus 120 degrees Celsius, which is our T sub 1. So this will equal to negative 40 degrees Celsius. So now that we have this value, we're simply just going to substitute it here. So our Q is equal to 850 joules per Celsius times negative 40 degrees Celsius. Cancel out the signs, And here's the interesting thing. Since it is negative, our final answer will also be negative. So the answer will be negative 34,000 joules. And since our answer is negative, that means that this reaction is exothermic because it is releasing heat into its surroundings. And that covers all the topics needed when it comes to the colligative properties of solutions, and as well as this quarter's general chemistry. So I think I was able to do it in an hour and a half, so that's great. Thank you for watching. And I hope that you're able to understand something. Even if you can't understand anything, as long as you're able to maybe understand a bit, I hope I was able to teach you something. And until then, I'll see you in the next one. So, bye.